In the last video, we talked generally about what system identification is. So in this video, let's put that knowledge to the test and use system identification to fit a linear model to data in a more practical situation. I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. To begin, let's first look at the system identification workflow that we sort of laid out in the first video, but we'll make a little more concrete here. Since system identification is a data-driven method, the first thing we need is to set up an experiment or a test to collect that data from the real system. We then need to choose a model structure that we want to fit to that data, which, as we'll see, isn't necessarily a straightforward task. And then we need to identify that model by actually fitting it to the data. And this step is an optimization process where each of the free parameters in the model are tweaked in such a way as to minimize a cost function. In many cases, the cost function is a least squares problem, where we try to minimize the sum of the square of the difference between what the model predicts and what the real data is. And then a gradient descent algorithm looks at how the cost changes as each free parameter is adjusted, and then moves them in the direction that lowers the cost. Note that you may or may not achieve the desired results. The estimation process may end prematurely due to it finding a local minima, or it may appear too good to be true due to overfitting. So between that and having to choose a good model structure to begin with, we may not end up with a model that best fits the data, and so the next step is to validate the model and see how well it performs. And if the criteria is not met, you may need to gather more data, or change the model structure, or tweak the identification algorithm settings and try again. This trial and error process continues until the criteria is met and you end up with a viable identified model. Let's walk through this workflow on a simple linear system identification example so that we have a baseline understanding that we can build on. And the first thing to do is to collect the data. And rather than get it from a real system, I'm just going to simulate a step response using a model. This model has a 2-pole and 1-0 transfer function with a 0.1 second transport delay on the input. So here, G_real is what I'm considering to be the real system. And I can generate the input and output data using this system. That's this step input and step response. All right, so with data in hand, I can now choose a model structure that I want to fit to this data. And for this, I'm going to assume that I don't know what the real structure of the system is and just try to reason through what it should be. I can see that the response to a step input overshoots, which indicates at least second order, and I can see that there's a slight delay after the step before the response starts to move. So I'm going to use TF_est to estimate a transfer function with 2 poles, no zeros, and an unknown delay time. This is the identification step, and it came back with this model. All right, now we can ask, is this a valid model? And here I'm comparing the real data with the model response, and we can see that it's about an 81% match. And this fit percentage is the normalized root mean squared error, which just shows how close the model response is to the measured response relative to the mean of the measured response. But even without this fit value, we can see that it doesn't quite look like the model structure I chose is capturing the right dynamics. And this was what I was talking about, where if you choose a poor model structure, it won't fit to your data very well. And if you don't know what the structure should be ahead of time, then this can just be a trial and error process. So now I want to revisit the model structure and see if I can get a better fit. However, instead of just changing the number of poles and zeros in the model, let me show you something really cool that you can do by estimating a state space model instead. First, let's separate the delay part of the problem from the linear model part. And I can use delay_est to estimate the number of samples that the output is delayed from the input, and then I'll just remove that delay from the output so that everything lines up in time. Now I use this aligned data to fit a state space model to it. But here is the cool part. Instead of choosing the model order myself, I can tell the function to fit multiple models, say between an order of 1 and 10, basically doing that trial and error process for me. When I run this function, a window pops up that shows the Hankel singular values of each of the models, where lower values means that there is low energy in at least one of the states of the model, and therefore is probably of a higher order than necessary to capture the dynamics. And we can see that it's showing that a second-order model is actually perfectly fine for our data. But with state-space representation, zeros come along as part of the package, which we left out of our transfer function model. So now I can select that second-order model and get a state-space equation. And I'm going to convert this back to a transfer function and add in the delay that we calculated earlier, and we arrive at the identified model of the system. And if I compare this with the data, we can see that it matches, well, almost perfectly. And in this case, it's pretty easy to tell that we identified a good model. But the only reason this was so easy was because the system we're identifying is perfectly linear with a pure transport delay. Plus, we were able to find the right model structure. And the data was not corrupted by noise or other disturbances, which is probably almost never the case in real life. So let's look at this exact same process again, but with more realistic data. And I'm going to loosely follow along with this MATLAB example, which I've linked to in the description. And I recommend checking it out if you want to follow along with what I'm doing. But I'm going to use a slightly modified version of it in order to tell the story that I want for this video. For this example, we're going to fit a model to a heat exchanger. A heat exchanger, as the name suggests, exchanges heat between two different mediums. And in this case, there's a product, like liquid in a tank, whose temperature is affected by coolant pipes that coil through the tank. So the coolant temperature is the input into this system, and that in turn affects the product temperature, which is the output. And the essential dynamics of this system can be modeled as a first-order transfer function, since the heat transfer rate from the product to the cooling coils is just a function of the temperature difference. Therefore, the change in product temperature is a function of the temperature itself plus the temperature of the input. Now, there is also delay in this system that comes from the fact that the coolant temperature sensor is some distance upstream from the heat exchanger, and when it registers a temperature change, it takes some time for that fluid to reach the product. So our candidate model structure is a first-order transfer function plus a delay term. However, heat is also gained or lost to the environment, and that is mostly based on the ambient temperature. And since we're not measuring the ambient temperature, we can treat this as a disturbance. The ambient temperature disturbance path is then in parallel with the main system dynamics. And this block diagram represents the model structure of our system. Now we want to try to fit this model to real data. So in this case, we were able to use physical intuition about the system to come up with the candidate model structure. This is the so-called gray box method. And if you're able to do this, it can simplify the workflow a lot, because now you've lowered the likelihood of having to do trial and error to find the right structure. All right, well, we got a little out of order in the flowchart by selecting the structure first, but let's go back and collect the data now. I've loaded in two different data sets. The first is the measured data that we'll use to estimate the model, which was collected from a series of step inputs. And the second data set is created from a different set of step inputs that we'll use to help validate the model. And notice how this isn't a perfect linear response. And this is going to make our linear model identification a little trickier to validate, which we'll see shortly. Now, just like before, we'll start by estimating the delay, and then use TFS to fit a transfer function with one pole and no zeros. This was the candidate model structure that we came up with. And we've got a model. Now, to validate this model, we can compare the real data with the model response, and this is the result. Now, visually, it looks pretty close, but the fit is about 73%. And if we compare this model against the validation data, the fit is now about 62%. So the model is missing what looks like the high-frequency content, as expected with a first-order model, but maybe it's also missing some essential first-order dynamics? It's a bit hard to say with this view. So the question might be, is this the best we can do with a linear model? For example, would a different model structure better represent the data? And to figure that out, we could try a higher-order model. And if we didn't have that physical intuition about our system, that might be a good idea. But since we know heat transfer in our problem is fundamentally a first-order linear process, I'm pretty confident that a first-order plus dead time model structure is sufficient. And so with a higher-order linear model, we just risk accidentally overfitting it to the training data and then doing even worse against the validation data. So at this point, a better question might be, can we account for this unmodeled part of the data in some way that gives us confidence that we modeled the linear part sufficiently? Well, it turns out that we can infer the answer, or at least gain some insight into the answer. And one way is by assuming that the unmodeled response comes from some random noise or random disturbance process. Let's go back to this block diagram. What I'm saying is that we could try to model this disturbance path as Gaussian white noise that is being filtered in some way through a function, which then corrupts the output of the system. For example, the disturbance temperature that comes from the unknown ambient temperature might change slowly, but fundamentally it's changing in a random way that can be modeled as filtered white noise. And if that's the case, then we could simultaneously fit a model to both the essential dynamics of the system and to the disturbances. And by accounting for the disturbance path, we can gain more confidence in the model of the system dynamics. So, how can we determine if our dynamics model is just plain wrong, or if the data is just influenced by a random disturbance process, or some combination of the two? Well, for one, we can use other model validation techniques to look to see if the errors are random in nature, or if they are correlated in some way. And I've left a good link in the description to a resource that describes in detail the whiteness of the prediction residuals and the correlation between those residuals and the input into the system. So I'm not going to go into detail here, but for the sake of this video, let me summarize quickly. All right, let's start with a set of data that we measured from a real system. This is the data that we want our model to be able to reproduce. So to see how well it does, we can initialize our model at the first data point and then predict what the output will be in the next step. And the difference between that prediction and the real data is the one-step prediction residual. And let me plot this residual down in this second graph. We can now initialize the model at the second time step and predict another step into the future and get that residual. And we can do this one-step prediction for the entire data sequence. Now what we're left with is this series of residuals over time. And here's the interesting part. We can look at the autocorrelation of these residuals. That's the correlation with themselves. If the residual values are correlated with themselves in some way, like we see here and a little bit here, then a part of the residual can't be chalked up to just random disturbances and noise, and therefore could have been predicted from the past data. So we're probably missing some dynamics in our model somewhere that could have captured this behavior. Now, on the other hand, instead of correlated residuals, let's say we got the model of the system perfect, but the output is corrupted by random noise or random disturbances. We can see that these random residuals are now not correlated at all. And this would indicate that the remaining non-modeled dynamics tend to be random in nature and not something that our linear model could capture. And therefore, we should account for these types of errors in some other way. Now, another thing we can do to pinpoint our modeling troubles is to check to see if the residual values are cross-correlated to the input in some way. Here I'm showing that the output was generated from this sort of impulse function. And now we can look to see if the residuals are correlated with this input. And there is some slight correlation here. But as we can see, it just about goes away when the residuals are random. And typically, high cross-correlation here means that there is a strong indication that the model that is mapping the input to the output is missing key dynamics, since the prediction errors tend to correlate to the input. Therefore, in general, if the residual error is correlated to the input, then we're missing something in our model in this path between the input and the output. And if that cross-correlation is low, but the autocorrelation of the residuals themselves is high, then that typically means that we are not fully accounting for the disturbances in this path here. So by interpreting these two tests, you can gain some insight into where your model is lacking fidelity. And again, check the resources that I list in the description for a fuller explanation of all of this. All right, now if we go back to the heat exchanger example and look at these residual correlations, we see that the cross correlation with input is low, but the autocorrelation is high. So we can probably conclude that we're missing dynamics in the disturbance path and not in the system model. And to test this theory, I'm setting up a process model, which is the same first order plus dead time model, but it also includes a disturbance model, which I'm going to fit to a first order autoregressive moving average, or ARMA1 model. Basically, it's Gaussian white noise that's been filtered through a one pole and one zero transfer function. And by fitting the dynamic model and the disturbance model at the same time, this is what we solved for. And now notice that the residuals are no longer correlated with themselves anywhere except at the point at zero lag. And the cross correlation is about zero across the board. So from this, we can conclude that we were able to fit the disturbance pretty well to an ARMA1 model, which then allowed us to fit a better first order plus dead time model to the dynamics. However, if we look at the comparison between this new model and the real data, it came back with about the same 73% fit. And furthermore, if we compare this new model with the validation dataset, it still has a fit that is in the low 60%. So it doesn't seem like we've actually improved on our model by accounting for the disturbances. In fact, if we compare the new model with the model that we estimated without disturbances, you'll see that they're practically identical. So you might be wondering, what was the point of estimating the disturbance at all if we got the same answer? Well, for one, this might not always be the case with your data. The disturbances in general might have a stronger impact on the system dynamic estimate, and by accounting for the disturbances, this can improve the overall model fit. And two, even though it didn't change, we now have a lot more confidence in this model since we were able to show low residual correlations once we accounted for the disturbances. So we've ended up with a model that we have a lot of confidence in. And we answered the question that about 60 to 70% fit is probably the best we can do. We can't get a better linear model fit because the external disturbance is contributing the rest of the dynamics to the output. Alright, so I hope this video has given you some things to think about when you're using system identification to fit a linear model to your own noisy data. And definitely check out this MATLAB example if you want to play around with these linear system identification techniques and learn a lot more about how they work. I've also posted my scripts if you want to see them as well. In the next video, we're going to look at the system identification process for nonlinear systems. So if you don't want to miss that, don't forget to subscribe to this channel. And if you want to check out my channel, Control System Lectures, I cover more control theory topics there as well. Thanks for watching, and I'll see you next time.